Hey guys, welcome back to day 24. We'll talk about entropy today and the second law of thermodynamics. The question begins, we'll start with the question, why do some things or some processes happen and others do not? So why do some things happen or some processes occur and some do not? So if I have H2O and I have H2O and we're going to call it solid H2O or ice, why does this go to water, H2O liquid, right, at 25 degrees Celsius? This is an always does this happen. Always ice going to water at 25. However, liquid water, so if I have H2O going to H2O, if I take liquid water to solid water, right, this is at 25 degrees Celsius, this is a never. We do not see that happen on Earth, right? Could it happen? I'm not even sure if it could happen if you really lowered the pressure down, really, like almost none, maybe. But on Earth, it's not going to happen. So why? Right? Why? Why does this happen? Let's go back to spontaneous change. An irreversible process that, under the specified conditions, occurs by itself. So a spontaneous change is an irreversible process that, under the specified conditions, and those conditions would be like pressure, volume, temperature, etc. Right? This occurs by itself. And here's the thing. It need not to occur quickly. It doesn't have to be fast. It just has to happen. So that's a spontaneous. And the question is, what drives this process? And the answer is entropy. S. So S is the symbol, and the basically what entropy is disorder. Disorder. Entropy is a thermodynamic function that increases with a number of equivalent ways, energetically equivalent ways, to arrange the components of a system. To achieve a particular state. So entropy, S, equals K, lowercase k, so that's the natural log of W. So S equals K times the ln of W. K, our little constant, it's the Boltzmann constant. And that happens to be R over NA, which is 8.3145 joules per Kelvin mole. 6.022 times 10 to the 23rd. And so that happens to be 1.38 times 10 to the negative 23 joules per Kelvin. That's the Boltzmann constant. W is equal to the number of microstates possible. So the number of microstates possible. Oh, sorry guys. It's a bowl. What's a microstate? So the microstate is the number of equivalent ways particles in the system can be arranged. The number of equivalent ways particles in a system can be arranged. Okay, so let's define macrostate and microstate. So the macrostate, macro, think macro big, micro small, right? The macrostate is the overall state of the system, right? Think about the given conditions. So this would be like pressure, volume, temperature, molarity, etc. That's a macrostate, the overall conditions. The microstate is the exact distribution of internal energy at any one instant among the particles that compose a system. You can think of it as a snapshot. Quick picture of the system. At a given time and is different from moment to moment. Okay, so for example, if I have acetic acid here, if I drew acetic acid, HCCOOH, this is acetic acid here, boom, 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 boom. We got bonding like that. That's one microstate. That's where the electrons are. We can also have acetic acid, HCCO, keep the H there, H. If I do it like this, that's another way to have acetic acid where I did not change the oxygens, if that makes sense. So we got the green oxygen here and the green oxygen there. So that oxygen atom didn't change. And the orange one's down here. First it's with the H, then it's without the H, right? Those are two different ways to arrange acetic acid. All right, and it can actually go back and forth. If that kind of makes sense to you, actually can do that. So that's what we're talking about. Another analogy, if you go into class, so let's say we were going to a seated classroom, and there were 18 chairs in this classroom, and you walk in, and there's one of you. You have 18 different spots you can sit. You can sit anywhere you want in these 18 chairs. And so there's 18 available spots. There's one student. And there's 18 ways to arrange you. If another student comes in, now there are still 18 spots. That's the Microstate. 18 seats is the Microstate, by the way. 18 seats is the Microstate. And there's now 2 students. And there are a lot of ways to arrange you. Right? There's quite many ways to arrange you. Now, the number of ways to arrange you is more. And so, because there's a lot more microstates, there's more ways to arrange you. So my example here, if we have 18 chairs, and there's one student, let's do one student. This would be 18 factorial divided by 17 factorial, which is 18. There's 18 ways for that one student. So W would be 18. If there's 2 students that come in, 18 chairs, 2 students, that's 18 factorial over 16 factorial, which would be 306 ways. So there's a lot more ways as soon as the second student comes in to arrange you guys. Because you can sit in the front 2 seats, the middle 2 seats, 1 row and a second row. There are a lot of different ways to arrange you. If 3 students come in, so look at this, 18 chairs, 3 students, so it'd be 18 over 15 factorial, which would be 4896, nearly 5,000 different ways to arrange you. That's crazy, right? And so there's a lot of ways. I mean, think about that. And just with 18 chairs and 2 students, you could meet every day. If you, let's say it was a 5-day-a-week class for 16 weeks, you could sit in different chairs, different arrangement each time, and not hit them all. Right? So this is the ways of disorder. So we get more and more people in there. There are more particles. There's more entropy. Right? There's more randomization availability. Because unlike a classroom, now here's the difference between the classroom. You're going to go into that classroom, you're going to pick a seat, and you're going to sit there every time if possible. And be mad if somebody's in your seat. Particles don't do that. They just go to places, right? And they go randomly. So like they'll hit all these states. So that's a big difference here. So entropy. Now, if I remove chairs, that's a new macro state. So if we go down to 16 chairs or 14 chairs or 5 chairs, totally changes the whole number of states possible, the macro state. So that's kind of entropy, right? That's our entropy. So things with small entropy would be something like a highly ordered system. So going back to your classroom, again, this is human behavior, but going back to your classroom, if you had 18 chairs, 18 students, and you guys would sit in the same seat each time, that'd be highly ordered. Nobody would be out of place. Everybody would be good. Very small entropy there because We know if somebody's not there because that seat's open. You don't even have to know their name. They know, oh, this person's absent today because that seat's empty, right? Because we associate the person with the seat. That's how ordered we are. Large entropy would be highly disordered systems. Think gases. So this would be a gas. This would be a solid in general. Okay. So I had two systems. Let's call I had system 1 and system 2. And let's say we had arbitrarily, that's just the y-axis for energy for system 1. Draw another axis for system 2. Oh, didn't draw the axis. Draw the arrow. Draw arrow for system 2. Not doing it. Try again. There it goes. So system 1 and system 2. If we have right here, and this is 2 joules, if I have a particle here that's red, and a particle here that's blue, right? That's a total. W is 1, and it's 4 joules total. Another way to look at this would be if I have there and there. So this is 3 joules, and this is 1 joule. If I have the red down here at 1 joule, and the blue at 3 joules, W equals 2. Because either the red has to be in the bottom at 1 joule, or the red has to be up top at 3 joules. And the blue's the opposite. So the total is 4 joules. But W is 2. So this is more entropy. That's more entropy. The state with the highest entropy has the greatest dispersal of energy. Energy can disperse through the system. We like that. Nature likes that. Okay. Second law of thermodynamics. For any spontaneous process, the entropy of the universe must increase. So it means the change in entropy of the universe is positive. How does this happen? Either the system increases in entropy, or the system liberates energy to create disorder in the surroundings. So if I have my system here in my universe, right, we can either have heat or work done, right? So if we're talking about heat transfer, Q, right? System, we got surroundings. We also have work. Now, for our purposes, we're going to look pretty much the system. Our system is going to be a reaction. Okay. Now, it'd be cool to be like a Ferrari engineer and be engineering a new braking system that's electromagnetic, that doesn't need braking. Like, that would be fun. And maybe that's what some of you might do. But for our purposes, we're looking just at basic chemical reactions right now. And so now our delta S, the change in entropy of the universe, will equal the change in entropy of the system or reaction. I'll put system down, but it's also our action would work fine, plus the change in entropy of the surroundings. If delta S universe is positive, the reaction is spontaneous. If it is negative, that means the reaction is non-spontaneous. Usually the reverse reaction is spontaneous. And lastly, if delta S of the universe is 0, we are at equilibrium. So all that stuff we did with equilibrium, it's going to keep coming on. So when we talk about solving and looking for things, the change in entropy for the system, right, it's a state function. So we're going to calculate very similar to delta H. So we look at delta S of the system. Okay. Delta S standard system is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. And these are in the same table you get delta H from. Also, delta S system or reaction equals S final minus S initial. Now, we have this system here. There's two things that can happen. So if I look at a reaction, that's my reaction, and these are my surroundings. The reaction can transfer heat, right, to the container. The surroundings could be the container. Right, and we're going to use delta H here, right, because we're going to assume constant pressure. All right, so we use delta H for our energy transfer at constant pressure. That means I can have an exothermic or an endothermic process. If it's an exothermic process, we release heat. Delta H is negative, which means delta S of the surroundings is positive. It's opposite. Endothermic, we absorb heat. Delta H is positive. That means delta S of the surroundings would be negative. So delta S of the surroundings is going to be equal to negative Q over the temperature in Kelvin. For our reactions at constant pressure, delta S of the surroundings would equal negative delta H of the reaction over T. Okay, so let's talk about this. The same quantity of heat causes less increase in disorder at higher temperatures. Okay? Which means the same amount of energy has a greater impact at lower temperature. So the same amount of energy has a greater impact at lower temperature. It's kind of like me and my story with money. If I didn't have much money, $100 is a huge amount of money for me. And that was a lot. It made a big difference. Well, as I got older and kids, family, $100, I'd still take it, but it doesn't make nearly the change that I did, let's say, when I was like 8. When you're 8, $100 is a big deal. Right? And some of you might now, $100 might be a huge deal. Hopefully you get to the point where $100 is not going to make you go bankrupt or not. Right, hopefully we get there. And that's why you're listening to this video, probably, watching this video. All right, so as you get more and more, earn over your years, hopefully $100 is not as big of an impact as it is when you're just starting out or, 16 years old. Makes a big deal. Same thing here with energy. So at low temperature, a little bit of heat makes a huge difference in the amount of entropy. At really very hot temperatures, a little bit of heat does not make that big of a difference. Now, if we look at delta S of the system or reaction, delta S of the surroundings, and delta S of the universe, right? If delta S of the system is positive, the surroundings is positive, the universe will always be positive. It will always be spontaneous. If the system's negative and the surroundings is positive, the system's negative, and let's go with the surroundings negative, universe will be negative, it will always be non-spontaneous. The difference happens when they have opposite signs. Plus, minus, minus, plus. Then it's these two are temperature dependent. And delta H is the driving force of the reaction. So that's kind of entropy. Entropy is this weird, it's kind of an abstract idea of disorder or randomness in a system. And the more disorder we have, the more randomness we have in the system, the universe likes it. Okay, and so it compels us to look at things a little bit differently than just the first law of thermodynamics. But before we get to summary, let's talk about the third law of thermodynamics. And the third law of thermodynamics is the entropy of a pure and perfect crystalline solid at 0 Kelvin is 0. W equals 1, so S equals 0. So that's, if you have a perfectly ordered crystal, a pure perfect diamond, no impurities, no atoms that are there that you can't even see that are, it's just perfect, all carbon, perfect diamond. And if you cool it down to 0 Kelvin, which is a theoretical limit, so I don't think you can. I think if you look at it, if you can observe it, I think you're more than 0 Kelvin. But if you could cool that diamond, that perfect diamond, down to 0 Kelvin, it would be 0 entropy. The electrons would be right where they're supposed to be. There'd be no molecular motion, no disorder. Unfortunately, that's not going to happen. All right. Okay. So we talk about reactions. A little snippet for when we get to reactions. The change in entropy for a reaction can be calculated from the standard entropy of each substance. Okay, so remember that our thermodynamic standard state. 25 degrees Celsius, 1 atmosphere, and 1 molar. Our entropy of O2, right, is not 0. So if you remember, the standard enthalpy of formation of O2 is 0. Entropies are not that way. Okay, so entropy is an extensive property. Right? It's an extensive property. It depends on the amount present. Just like with going back to our seating arrangement. If you have lots of seats or a little bit of seats, lots of students, a little bit of students. So if you have a lot of students, there's more entropy because of how much is present versus only a couple of you or one of you. Same thing here. So if we look at the terms, the lens of heat to work, let's summarize, right, thermodynamics. In terms of heat to work. Because that's what we want. We want our heat to work. First law is the best we can do is break even. Right? If I have 500 kilojoules of chemical potential energy, the most I can get out is 500 kilojoules. That makes sense. The second law says you cannot break even. Well, that's kind of nice. Not. So the second law of thermodynamics compels us to use energy. I'm going to quote, use energy in such a way that the entropy increases each time it's converted. Increases each time energy is converted. So the second law prevents higher forms of energy or large entropy from being spontaneously reduced into lower, more useful forms of energy. Lower, more useful forms of energy. Which is low entropy. What does that mean? Think about eating a steak. That steak has a very, very big molecules, right? Or most of our food, even an apple, banana, big molecules, all right, highly ordered, contain energy in them. We eat them, and we take that energy out by rearranging those molecules and atoms, and redistributing those electrons, and what we produce has no more packed energy. It's more dispersed, right? So gasoline, you take your gasoline in your car and you burn the gasoline. You go from compact energy in the gasoline to dispersed energy out into the world. And so we take these highly packed, dense forms of energy, right? And gasoline's are very dense. This is why we still use gasoline. It's very energy dense. It's way more energy dense than batteries can get. So you can go way further on gasoline than you can on a battery. And also gasoline cars are much cheaper. That's the other reason why people use them. So this second law says we have very energy dense to energy spread out. That's the way we transfer it. And we always lose some. That's where your book's heat tax comes in, because when we're talking about heat to work, it's assuming that you have a exothermic or an exothermic reaction to make heat to work. Obviously, you cannot heat tax an endothermic reaction. So if it absorbs heat, you're not going to tax it either, right? It's just not going to happen. You don't have the ability to tax something that's not producing anything. But when we look at heat to work, we have energy dense to energy dispersed. So compact energy, right, like a steak, gasoline, these things, goes into energy that's spread out. Smaller molecules that are less dense. And that's entropy. And then we're going to do some examples of entropy, and then in the next video we'll actually talk about how much is used and how this all works when we talk about free energy. First, let's do some problems. Number 30. Suppose two systems, each composed of three particles represented by the circles, have 30 joules of energy. How many energy equivalent ways can you distribute the particles in each system, and which has greater entropy? Well, here I have 10 joules, one state, one macrostate at 10 joules, so W equals 1. System B, I have 3 particles, 3 states, so that's going to be 3 factorial, or 6 ways. 6 ways to do this. W equals 6. So system B has greater entropy. Because the red could be here or here, right? We could draw them out. So I could have a red there, and then the blue up top, and the green on the bottom. So that's a second way. You do the red on the bottom here, keep the blue in the middle, and have the green up top. So there's 3. I want to keep the red on the bottom again, but instead of having the blue in the middle, I'm going to have the green in the middle, and then that means the blue's on top. So 1, 2, 3, 4. So another red up top, and green in the middle, and blue on the bottom. There's 5, and another one. I got 2 there. Another red in the middle, and with red in the middle, I had green down there. So I need the blue down here, and green up top. So those are the 6 ways to do it. These are the 6 ways to do this vertically. 1, 2, 3, 4, 5, 6. So there's 6 ways to arrange these 3 particles in this system. Problem 34. We are looking at no calculations. Determine the sign of system surroundings for each chemical reaction, and then predict what, if any, were spontaneous. Okay, so delta S of the system, a reaction. For A, I have 3 moles of gas going to 2 moles of gas. Right, so 3 moles of gas we're going to convert to 2 moles of gas. So delta S system probably is going to be negative, right? Because 3 moles would be more entropy than 2 moles. The surroundings is going to be the opposite sign of delta H. So that's going to be positive. The reaction spontaneous, where? Is it going to be high temperature or low temperature? So where is temperature at? Is it in the system or is it in the surroundings? And it shows up in the surroundings. So delta S surroundings is negative delta H Rxn over T. So as T gets bigger, what happens to this number? It gets smaller. As this number gets smaller, this positive number gets smaller, eventually it'll be a smaller value than this negative number. So this will be spontaneous at low temperatures. That's A. B, delta S of the system or reaction is going to be, I have 2 going to 3. So that's going to be positive. Delta S of my surroundings will be, well, opposite sign of delta H is going to be negative. And so the opposite thing's happening here. However, here it's positive, right? So that's going to be a negative number. So delta S surroundings is negative delta H over T. So delta S is negative. As T gets bigger and bigger and bigger, again, this number gets smaller and smaller and smaller. So this will be spontaneous at higher temperatures. Spontaneous at higher. Possibly. Right, these are all possibly. It depends on the order of magnitude of these numbers, but possibly. C. We have H2O2 going to H2O. So that means delta S of the system, I got 3 moles to 2 moles, is negative. The surroundings, opposite sign, delta S of the surroundings, would be positive because the opposite sign delta H. And just like the first one, it's going to be spontaneous at lower temps. And we don't know exactly what lower, it doesn't have to be below freezing or anything like that. It's just a lower temperature. There's a certain temperature, and below we're spontaneous, and then it hits a certain temperature and it becomes no longer spontaneous. That could be a very high temperature in general. We don't know. We just know that this is the principles. And finally, D. We got 1 going to 2. Oh, we got 1 mole of gas going to 1 mole of gas and a solid. All right. But because we have a solid, delta S system is going to be negative. Also, the surroundings is going to be delta S surroundings negative, which means we're going to be always non-spontaneous. Because this solid, solids are way more ordered than gases. So that's why this, even though it's going from 1 thing to 2, because that carbon's a solid, a lot more, we're becoming way more ordered. 238 here. Given the values of delta H, delta S, and T, determine delta S universe and predict whether or not each reaction is spontaneous. So it gives us delta S right off the bat. So delta S here, well, first, delta S universe is delta S system, a reaction. I'll put reaction because it's down here. Reaction plus delta S surroundings. And delta S surrounding is negative delta H reaction over T. I want to point some out though. See how delta H is measured in kilojoules? Usually S's are in joules, so they're 1,000 times different. And that's okay. For A, we have delta S system, which is negative 157 joules per Kelvin. Plus, now delta H is negative 95,000 joules, and the temperature is 298 Kelvin. There we go. And if I do that math, I think I get 161 joules per Kelvin, which is a positive number. So that means A would be spontaneous. For B, delta S system is negative 157 again, joules per Kelvin. Plus, now it's delta H is still negative 95,000 joules. Temperature is now 855. Well, that's going to make this term different. And I don't know if this is, I forgot this sign. I apologize. Because delta S's surroundings is negative delta H. What do we get there? I think I get negative 46 joules per Kelvin. Make it non-spontaneous. For C, we have still negative 157. 7 joules per Kelvin. Right, plus negative, and then we got to put delta H in there, and delta H is positive 95,000 joules divided by the temperature of 298. Doing that, I get negative 476. joules per Kelvin, which would be non-spontaneous. And lastly, D. Now I have positive 157 joules per Kelvin plus, and it's negative, delta H happens to be 95, again negative 95,000 joules. And the temperature is 398. But that's a positive number, so this is going to be positive, and it's 396 joules per Kelvin, and it is spontaneous. Right? So I'm just plugging this in here, so it's plus the negative delta H. So that's why there's 3 signs there, but that's why. That is 38. 36, a reaction has delta H 112 negative kilojoules per mole, or kilojoules, and delta S 354. At what temperature is the change in entropy for the reaction equal to the change in entropy? Okay, let's look at this. Delta S system plus delta S surroundings equals 0. Delta S system equals negative delta S surroundings. Delta S system equals negative delta H reaction over T. Delta S system equals delta H over T, which that means T times delta S system is delta H of the reaction. So that gives me T equaling delta H of my reaction all over delta S of my system, or reaction. Okay, so my temperature then, delta H is negative 112 kilojoules. Delta H is 112 kilojoules, 112,000 joules, divided by 354 joules per Kelvin, and I get 316 Kelvin is my temperature. That concludes entropy. Next video, we'll go into Gibbs free energy. Take care, guys.